Welcome to Google Cloud Next on Air. In this session, we'll be discussing Major League Baseball's data warehouse modernization journey. I'm Ryan McDowell, Cloud Data Engineer from Google, and joining me today is Rob Goretsky, VP of Data Engineering at Major League Baseball. Today, we'll be taking a look at general migration strategy for cloud data warehouse migrations, and then deep dive into how and why Major League Baseball moved their data warehouse to BigQuery. Starting off with the overall strategy of data warehouse migrations to the cloud. We've heard from our customers that traditional data warehouses are causing tons of pain as they're unable to keep up with today's analytic demand. There's tremendous complexity with scaling on demand, and this is compounded by the inability of their incumbent technology to keep up with data growth. Traditional data warehouses were built for batch paradigms, and not for today's world, where by 2025, about 1/4 of data will be streaming in nature. Access restrictions and data silos on-premise inhibit data sharing and collaboration. Existing legacy solutions have the inability to take advantage of emerging technologies such as AI in real time, and you need to move data out of your data warehouse into complex, fragile, or niche systems that require PhDs to operate. Finally, legacy data warehouses are extremely expensive to purchase and maintain. So how does BigQuery address these challenges? BigQuery allows you to store vast amounts of data. With BigQuery, Telegraph Media Group reduced their query time from hours to minutes, with up to 4 terabytes of data processed in less than 1 minute. Blue Apron streams 140 million events per day with BigQuery. This has helped them accelerate business decisions by 1 day to near real time to better manage food inventory and delivery. Home Depot is able to empower business units to create their own BigQuery projects and reduce dependency on IT budgeting for additional data warehouse capacity. 20th Century Fox uses BigQuery to run analytics to pull data from DoubleClick and YouTube, and uses TensorFlow to do audience analysis on film scripts and track content patterns that may better predict what resonates with audiences. HSBC needed to cost-effectively upgrade their aging Teradata environment and across multiple regulatory jurisdictions. By moving to BigQuery, they're able to save millions over 7 years. So how should you be thinking about your data warehouse modernization strategy? This diagram shows a high-level legacy architecture from before the migration. It illustrates the catalog of available data sources, legacy data pipelines, legacy operational pipelines, and feedback loops. Additionally, legacy BI reports and the dashboards that are accessed by your end users. In order to migrate a legacy data warehouse architecture to BigQuery, we first need to go about decomposing the migration such that we aren't left with a risky big bang cutover. At Google Cloud, we generally think about data warehouse migrations through the lens of the following framework. First, through cloud foundations, where we set the foundational cloud infrastructure, including network, IAM, and security. Then risk assessment and mitigation, where we evaluate the operational risk of the migration and then develop detailed mitigation plans. Third, the migration, where we actually execute the migration, comprising of various steps. Then change management and learning, setting up a center of excellence within your organization such that when the new environment is cut over, users are confident from day one. During the migration, we generally approach it from an iterative standpoint. First, we'll assess and plan the migration based on the source environment and design the destination environment. Then we'll work through an iterative process going workload by workload or subject area by subject area, where we work on migrating those workloads from the source system to the destination system. This generally comprises of enterprise setup and security mapping, migrating schema and data using BigQuery DTS, translating queries using some of our partner tools, migrating business apps, migrating upstream pipelines, verification and validation to ensure that once the environment is cut over, that users are getting the same results on top of the same data sets that they had when they had on their source system, performance tuning, and then of course, report and scale testing. Now I'll turn it over to Rob to take us through how Major League Baseball completed their migration journey.
Thank you, Ryan. My name's Rob Goretsky, and I'm the VP of Data Engineering at Major League Baseball. Today I'm going to talk about Major League Baseball's migration from Teradata to BigQuery including the motivations for migration, the actual migration process itself, and the capabilities we unlocked when we completed this migration. So, as a bit of a background, I oversee the fan data engineering and business intelligence teams at Major League Baseball. We work with fan transaction and interaction data generated by internally developed applications, including MLB.com and the 30 Major League Baseball club websites, and our MLB and ballpark apps, and third party sites such as Ticketmaster, Tickets.com, StubHub, and Fanatics. My team doesn't work directly with player stats or on field data such as StatCast. That's the domain of our baseball data team at Major League Baseball. But we do work with the more traditional user engagement data to ensure that we understand our fans and can bring them closer to the game of baseball. This includes personalizing and targeting marketing and fan experiences on our website and on our apps, and sharing our centralized data with all 30 Major League Baseball clubs in our project known as Wheelhouse. We have over 350 data pipelines that have been developed over the last 10 plus years. Most of our data sets are not what I'd consider to be really big data. For example, a data set containing every ticket sale only contains about 80 million rows per year for a couple hundred gigabytes of data. That said, we do have a few very large data sets generated by user interactions on our website and apps. These are highly trafficked, and we collect every user interaction and store it in our data warehouse platform. In addition, many of the medium-sized data sets, such as ticket sales, turn out to be pretty complicated in terms of the modeling and validation due to the various ways fans can purchase, exchange, resell, transfer, and ultimately share and use these items. Before our migration to BigQuery, we used Teradata as our data warehouse platform. We ran data pipelines using Informatica and Airflow. MLB employees could access Teradata directly by connecting using SQL and using our BI platform Looker, but we didn't have a means to open up access directly to Teradata for all 30 Major League Baseball clubs without major performance and security implications. So we set up Airflow pipelines to essentially copy data from Teradata to S3 in 30 separate files, one per club, per dataset, to allow clubs to access that data via S3 and Athena. This setup presented several challenges. The major challenge with sharing data with clubs was that we were copying data. So when we're copying data, you need to properly identify which data has changed each day if you want to do an incremental copy. And this was challenging in cases where we had late arriving data or corrections to make to the data that happened after the fact, which was especially common with our ticketing data sets. In addition, if we wanted to evolve the schema that we shared with clubs, either by adding fields or changing data types, that often would then require us to recopy all historical data out to the club, which can be time consuming and error prone itself. In addition, if we had a correction to make, we often would need to circulate that on a changelog so that clubs would be aware that we've made a change to the data, that they should refetch perhaps older data files that we had published. This process was also very much a one-way street. Clubs didn't have a way to share data back with us in a way that we could easily query and that would automatically set up schemas for us to work with. As our data sources started to become more and more real time, another issue with this setup was that the system to share data was itself batch-based. So even if we were ingesting data in real time, to share the data back with clubs involved making a copy perhaps every hour or even more frequently every 5 minutes, but we never really hit a real-time cadence where clubs could see the data as it happened. Other major challenges outside of the data sharing with working with Teradata included the operational support overhead. We maintained a full-time DBA team who helped us with the traditional DBA tasks such as resolving performance issues, monitoring for database deadlocks and long-running queries, resolving backup issues, and we spent a lot of time and effort trying to continue to refine that part of the system when really that wasn't our core concern. Our core concern was ultimately providing business data and analytics to our organization. With respect to performance, we often found that in spite of our best efforts to implement proper workload management and tuning, we often would have one bad apple spoiling the bunch. A single well-intentioned user query that ate up the entire spool space or otherwise brought the system to its knees was fairly common and something that we had to deal with all the time. Another issue as we started looking at scaling our system on Teradata was that the compute and storage were tightly coupled. This meant that if we wanted to consider bringing in some of the very, very large data sets, such as our clickstream, we couldn't do so without also linearly increasing our compute, which came at much additional cost that perhaps didn't make sense for us overall. Furthermore, we found that integration with third-party tools and apps was limited. When we were looking to integrate with new BI platforms or data science tools or analytics tools, often their support for Teradata was mediocre at best. So we ran a project to fully migrate Teradata from BigQuery from May through November 2019. So we ran this entire project in about 7 months' time. At a high level, the work involved setting up data replications from Teradata to BigQuery, and then iterating through the conversion of ETL jobs and reports. We needed to continue to support live reporting and agreed that a big bang cutover happening all at once was not going to be feasible or desirable for us. We instead wanted to take things in chunks and ensure that along the way we were validating that BigQuery was performing as expected and that data was loading properly and matching up with our expectations. So, in order to determine the order in which to attack converting and migrating all of our ETL jobs, we built a dependency map that took a look at which tables and ETL jobs were upstream and downstream from each other. Jobs that were less entangled because they were on the leaf nodes in this diagram had fewer downstream dependencies and therefore could be migrated first. So we worked outside in, if you will, on this diagram where we took those things that had the fewest downstream dependencies, migrated them first, and then continued to work our way inwards. We set up hundreds of replication jobs using Apache Airflow very early on in our project and throughout the project as needed as new tables arose. One of the more time consuming tasks about this was determining exactly which upstream process we should wait for before replicating data to BigQuery. But we consider this critical for our success because we wanted BigQuery to be as close as possible to being a perfect match of what was in Teradata. So, for example, if we get a daily load of StubHub data and that arrived into Teradata at 9 o'clock a.m., we were hoping that we could have it in BigQuery by 9:01 a.m. So this is not a hot replication. It's not necessarily what you might consider a real-time replication, but it was basically close enough that all of our analysts, data scientists, report builders, BI team could immediately start using BigQuery very early on in the project for all of their new work. This ensured basically that all the data was essentially in BigQuery as fresh as it was in Teradata. So as a result of this carefully timed setup for replication, these data stakeholder teams were able to start developing new queries and processes on BigQuery very early on. This was great because otherwise, if teams were continuing to build new work on Teradata during the 7-month migration, we might have another 7 months worth of migration to do afterwards, and we might never finish the project. So it was important for us that we could sort of draw a line in the sand and say to all of these stakeholder teams, only build new things on BigQuery. We're going to replicate all the data you need to work on your process. So for example, for the data science team, we're going to make sure that all the ticket sales data that you need to do predictive analytics is there in BigQuery. So it's going to look and feel just like it does in Teradata, but be available to you at the same time so that everything new you build today, you can start building on BigQuery. In the back end, we continued migrating the ETL jobs themselves, but by simply having replication and unlock the ability for most teams to think about BigQuery as a live production system right away. As we converted ETL jobs, having replication in place also allowed us to ensure that we could do table validation and match results between the result of output from Teradata and BigQuery. So in order to proceed with ETL conversion, we focused on developing a recipe that could be followed by data engineers without them having advanced knowledge of any of the business or domain logic that were contained within that pipeline. So we started off looking at steps that could be automated, and we spent some time upfront developing tooling to automate those processes. For example, we wrote shell or Python scripts that would simply pull pieces of SQL out of parts of our code so that we could quickly identify which pieces needed to be translated. We also looked for cases where there were Teradata specific function calls or Teradata specific commands being issued, and we were able to pull those out and kind of translate those in mass. So this meant that for the first month or so of our project, we weren't necessarily doing an end-to-end ETL conversion just yet, but we were kind of building out the tools that would enable us to then move very quickly through all of the others. So once we got through building out a lot of the automation, the remaining steps was a majority of the project, and it was done by our data engineers. This involved places where either it was too difficult to build automation for something, or because we wanted to have validation done by a human who could look over something and ensure that it passed proper sanity checks. Also, working with Informatica, we found that there was no easy way to automate, mass changes. So a lot of those involved clicking through the interface and just manually making changes in the GUI. So with respect to automated components, one tool that helped us immensely was a SQL Transpiler tool by a company called CompilerWorks. This tool accepts Teradata SQL as input and then outputs BigQuery SQL. So while minor SQL differences such as function name changes or small syntax changes could have been resolved by a simple regex search and replace, more complex cases involves having a deeper understanding of the SQL structure and the data types that underlie them. Here's a really common case that we had that used the Teradata specific qualify clause. The CompilerWorks tool was able to pull the clause used within qualify and rewrite the query as an inner query. Doing this at hand would have been error prone at best. Another major advantage we found when using the CompilerWorks tool is that it became aware of the actual schema itself, including the data types. So BigQuery is pretty specific about data types. For example, if a field has a data type of integer, it may not allow you to directly insert a numeric value without casting it to an integer. Teradata was a bit more lax about this. So this is the kind of thing that a translation normally would trip up on time and time again. But CompilerWorks' tool, being aware of the data type of a column, when it parsed and read the SQL, it was actually able to automatically apply the proper cast or conversion statement to it for us so that the syntax would be valid and would run immediately. When we were done converting an ETL pipeline, we'd continue running the original pipeline in Teradata, but we'd run the converted pipeline side by side in a prod parallel environment. In this diagram here, we see the Airflow DAG diagram of our original ETL with Teradata operators embedded within. And on the right-hand side, we see the exact same pipeline with BigQuery operators embedded within. And we set these up to run in two separate environments, but at generally the same time of day with the same input data, so that we could basically do a side-by-side check that the output data would match. To further assist us with this table validation, we looked in the marketplace for tools that would essentially allow us to run a diff between two tables, similar to how you run a diff when you're using Git to look at code review or pull request reviews. We couldn't find anything that fit our needs exactly in terms of allowing us to do a table to table comparison by joining on the primary key and then telling us if rows were missing from one table or another, or if rows had fields that differed in one table or another. So we built our own tool. Our own tool essentially ran queries and generated SQL for us on BigQuery to take the output of the replicated Teradata ETL and compare that with the output of the BigQuery ETL. This would quickly surface to us if there were either differences in the row count or in rows missing on one side or the other, or if there were field differences. At this point, this was one of the few pieces of the project that really required domain and analyst expertise, because if the diff tool showed differences, and it often would show some differences, we needed to make a business decision about whether those differences in the output were relevant for our use case. For example, if there was a field that simply had a created date or a timestamp, we would expect those would be slightly different between Teradata and BigQuery simply because of the slightly different runtime when those jobs completed. However, if there was a field such as a financial charge value, we would expect that generally those should match up exactly. So if there was a difference in those and it was significant, we would need to dig in further to see where in the pipeline something was either mistranslated or something perhaps was thrown off for some other reason. So having a tool like this allowed us to have the data engineers spit out conformed output that then we could pass to analysts and end users and more experienced users of the business analytics side to help us understand what the differences were. So taking a look again at sort of where we went, we took a look before at our data architecture before our BigQuery migration, including this middle layer where we had landing data as a copy for club data access in our wheelhouse project. After BigQuery migration, you see that we've removed that middle layer completely. Consumers of data, whether they are at clubs outside of our network or internal users or our data science or other constituent teams, are all looking at the exact same copy of the data. There is not a second copy made of any data. This means that if we load data in real time, it's available to those consumers in real time. And it also means that we don't have to deal with all the discrepancies that arise by making copies of data. So we mentioned a few of the benefits here, and we're going to summarize them here. With respect to democratization of data, I will do a live demo here in a few moments to show how we could use the BigQuery tools to very easily share data and securely ensure that we only share a subset of data with the proper stakeholders. With respect to performance and scale, we saw that some of our large queries had a 50% reduction in runtime without really any additional work done on our end. And similarly, we saw that certain data sets, such as our clickstream data, which consist of over 300 terabytes a year in uncompressed data, were able to be loaded into BigQuery, whereas previously we couldn't even consider doing something like that. So we instead needed to keep really large data sets like those in separate silos within a Hadoop ecosystem to process them. Having them all in one place was one of the single biggest user requests that we had gotten because users often want to join the clickstream data with other data sets, such as our ticketing or shop data. For security, instead of having to have separate user rights and roles and credentials, all of this is centrally managed by our InfoSec team by way of our integration with Okta and G Suite. So users are set up with groups within Okta, and those flow automatically into G Suite, which then flows automatically into BigQuery roles and responsibilities. This means we don't have to have any time spent on setting passwords, worrying about who has compromised access, who might otherwise leave the organization. All of it is set up centrally in one place. Um, Developer happiness is really a key one for me and my team, in that we just found that everybody who worked with the system sort of understood things right away with it and generally had less gotchas than what they did with Teradata. More specifically, we found that one of the biggest advantages is that we can often Google if we're not sure about exactly how to do something and find a helpful Stack Overflow answer almost right away. This wasn't necessarily the case with Teradata, which was generally the domain of enterprise companies and larger customers, and really wasn't as widely available to the masses as something like BigQuery is. Where with BigQuery, there's a free tier that any engineer can jump in and try things out with it. It just means that there's a wider mind share for it. It means that there's more documentation and more community support for it. And we find that helpful time and time again. With respect to features, we're finding that features are consistently added that help us out without breaking anything for us and without requiring any downtime for upgrades. With Teradata, we were sort of pinned to a specific version for several years at a time because an upgrade was a major process. I mean, for us with BigQuery, we just take a look at our system one morning and we see release notes and there's new features, and it's like opening a goodie bag. You immediately have some new toys to play with every day. Um, so, with respect to flexibility, we found that early on in our testing, we didn't want to make a big commitment about going with BigQuery, but we loved that we could use the on demand model to load some data, even some of our larger data sets, and try things out without having to make any upfront commitment. The operational overhead has been significantly reduced. Right now, backups are automatic, and one of the things that our team really loves is the ability to simply ask BigQuery to present a copy of a table anytime in the last 7 days. So if you're trying to validate a data load issue that happened last night, you can simply ask BigQuery to present the copy of the table from yesterday, and you can take a look at what changed. Similarly, if you've ever accidentally dropped a production table, and I know none of us have ever done that, you can easily undelete a table for up to 3 days with a single SQL command. So there's no need to run to the DBA and ask for a tape backup and have your heart skip a beat as you think about the implications of what's happened there. BigQuery kind of handles all of that for us in a really easy to use way. And finally, with respect to cost, again, the on-demand pricing allowed us to start things up at a low run rate. And then once we found what we stabilized at, we could basically purchase reserve slots and make sure that our cost was fixed going forward, that we wouldn't have sudden spikes. So now I'm going to jump into a live demo where I'm going to show how we democratize data at MLB. And in this case, I'm going to walk through an example where we are going to take a data set that contains data for all 30 Major League Baseball clubs and show how we would share it with just one of those clubs while applying security to ensure that that club can only see their own data. I'm then going to jump in from the perspective of a single club, in this case, the Yankees, and show how that club is able to access that data and even run queries with their own data, combining and joining with that data. To demonstrate how BigQuery's dataset sharing and authorized views allowed us to democratize data access at Major League Baseball, I'm going to walk through a small example here. I'm in the BigQuery console logged in as a Major League Baseball employee, so I have access to data across all 30 teams. For example, here I've set up a small dummy schema of a tickets fact table that contains one row per ticket sale transaction. Um, as Major League Baseball, we have access to all 30 teams' data, and one of our goals here is to ensure that we share that data with each of the 30 clubs so that they can make their own local business decisions. So the goal would be to share the Giants data with just the Giants and the White Sox data with just the White Sox. In our first iteration of Wheelhouse data sharing, we accomplished this by setting up 30 copies of the data each day. So we would run queries to segment out the data and pull all of the Giants data and put that in one file. Then we'd pull data for the White Sox and put that in another file. This involved making copies of the data, which incurs issues when perhaps you have data that has been updated later on after the file was produced, perhaps, other data synchronization issues, and just other challenges in making sure that you stay in sync with what you've copied out. So with BigQuery, this gets a lot easier. So to demonstrate this, first of all, logged in as Major League Baseball, I can do a demo query to show that I can run something like a sum of the quantity from this table across all 30 teams. So as Major League Baseball, I can see the sum of the quantity broken down by the team name, for example. And we can see that I do have access here as Major League Baseball to all 30 of the clubs' data. So now if I want to just share data with the Yankees, for example, we should be giving them access to just the slice of the data pertinent to them. The way we accomplish that is by creating a data set that we share data with the Yankees in. Assuming one doesn't already exist, I can go into BigQuery's console and simply set up a data set that we will use for sharing with the Yankees. And within that data set, I'm going to create a view, and this is a standard SQL view that's just going to say we're going to create a view of next demo Yankees tickets as select star from the parent data set where the team name is the Yankees. So we're just going to say where the team name is equal to Yankees. So this is a standard SQL view, and we'll see that it gets created, and we can check it out that the DDL is available here for us, and it's our pretty traditional SQL view where it just gives access to that slice of the data. Most data warehouse systems and database systems do not allow you to share access to the view without sharing access to the underlying table. And this is where BigQuery's authorized view differs. So normally I couldn't share this view without actually giving access to the entire base table, which we wouldn't want to do because we want to give the Yankees only access to their subset of the data. So all we have to do here to enable this functionality is on our parent data set, set up the authorized view to say that this new view that we've created in the child data set is authorized to access the parent data set. So in this case here, we're going to say that the next demo Yankees view is authorized to access the next demo sales, the parent data set. With that in place, all I now need to do is figure out who I want to share the data with. And this works very similarly to Google Drive or Google Docs sharing, where you simply provide a list of G Suite email addresses or G Suite groups. For this demo, I'm going to be using just a single dummy email address I set up, but in production, we actually use G Suite groups to enable entire groups of users at a time that are managed locally by the clubs. So all I have to do to share data is give it a list of email addresses that I want to share with. So I'll use my dummy email address here of yankeesstaff@gmail.com. And I tell it that I want to give access just to view the data, not to modify it, not to modify the DDL. It's a read-only access that I'm providing here. And much like any other sort of Google Suite sharing, that's it, we're done. So now we can see that we immediately have given access to a set of users or a user. So I'm going to switch gears here now. I'm going to switch over my browser window to see what the Yankees would see. I'm logged in here on this browser window as the Yankees staff. And initially, I would have had access to perhaps nothing if nothing had been shared with me yet from Major League Baseball centrally. But if I refresh my screen now, I have access right away to that data set that's been given to me here. So I have this tickets data set here, and I can start running queries on it right away. For example, the same sum of the quantity that I was running on the parents data set, I can run here all the same, and I'll see here that as the Yankees user, I'm only getting access to that slice of data that's pertinent to the Yankees. So in this case here, it's just that 10,000 rows. Um, what makes this even more powerful is that I can bring my own data that I may have locally and not shared with Major League Baseball, and I can join that across these data sets. So there's no barriers here of data silos where data in different data sets can't be joined. If you have access to data, no matter what the data set is, you can join across it. So for my example here, let's imagine the Yankees have a small local sheet of promotions they are running, and they want to analyze which of those promotions generated the most sales. So if this is a sheet they may have in a CSV, they could go ahead and use BigQuery's UI to very easily upload that data from the CSV. We point to that CSV, we give it a table name here, we'll call it promos, and we'll tell it to automatically detect the schema. And just like that, within a few moments there, we will have a table created for us locally. This would be a table that the Yankees have access to that otherwise is not shared anywhere else. Now, the join could be written that combines those two things together. So I've written this query up here that says, let's take the data that Major League Baseball would have shared with us in the tickets data set, and we're going to do a join with the promos data on the game date. And this will allow us to run that query that crosses those two data sets and sees which promotion has the highest overall quantity sold. So in this example here, we see that the highest quantity sold was a t-shirt. That led to the most quantity sold, other than null promotions, which were there because perhaps we didn't fill in all the promo data. So you can see how this paradigm of being able to join across data sets you're authorized to allows you to have different access patterns for data while still allowing centralized querying across them.
Thanks, Rob, and thank you for joining us for Google Cloud Next. Be sure to check out some of our other great data analytics sessions. Thank you.